So, this is going to be our first this problem solving session for mass transfer. So, we will start with the diffusion and interface mass transfer, and progressively we will go forward maybe in the next or the next to next session for other mass exchangers from this absorption to extraction to humidification, then distillation, etc. Right. So, for the time being, I have excluded this coverage of adsorption and membrane separation, which this membrane separation is a new topic for 2021 GET. So, I will discuss it. Maybe in the next sessions you will be able to get this adsorption and this membrane separation. So, anyway, so first let us solve an interesting problem. It is 2015, simply 1 marks problem, but the problem is interesting. What is that? A spherical naphthalene ball of 2 millimeter diameter is subliming very slowly in a stagnant tear at 25 degree. Right? The change in the size of the ball during the sublimation can be neglected. So, dP remains constant. The diffusivity of naphthalene at here, so d naphthalene here at 25 degree Celsius, that is given to be 1.1 into 10 to the power minus 6 meter square per second. So, what is asked? The value of mass transfer coefficient K is B into 10 to the power minus 5 meter per second. Now, we have to solve for B. That is the question, 1 mark question 2015. So, you see its diffusivity is given, diameter is given, air temperature is given, and the K, the form of mathematical form of K is given. So, you have to hit the strategy of solving this problem simply upon thinking about the mass transfer coefficient and what will be the mass transfer coefficient, how we can solve for the mass transfer coefficient. Immediately we have to think of Sherwood number, right. And just like Nusselt number is equal to 2 for spherical objects, conductive heat transport in air, we have proved that. Similarly here, the Sherwood number will be equal to 2, right. So, our entry point in solution is considering the Sherwood number is equal to 2, and Sherwood number is equal to Kc into dP divided by capital D, and that is equal to 2. So, Kc and dP is 2 millimeter. So, 2 into 10 to the power minus 3, right, and diffusivity 1.1 into 10 to the power minus 6, and that is equal to 2. Okay. So, yeah. So, diffusivity is 1.1 into 10 to the power minus 6, and what will happen? This 2 cancels out. So, Kc is equal to 1.1 into 10 to the power minus 3, right. And from there you can conclude that what will be the value, because if I write 10 to the power minus 5, we have to multiply it by 100, right. So, it is 110 meter per second, right. So, the crux of solving this problem is Sherwood number is equal to 2, because here what is important to note that it is stagnant air, right. So, it is purely diffusion, and from there we can calculate Kc. Next, you see another problem. It's 2004 2 marks problem. 2 marks problem. Right. If the constants a n are suitably chosen so as to satisfy the initial condition and n is an integer, which, so a n a constant and n is an integer, right. That is the first statement. Which of the following is a valid solution for unsteady one-dimensional diffusion equation? The equation is given, which is del C del T is equal to capital T into del square C del x square, right. In the domain between 0 to L, and the boundary conditions are x equal to 0, C equal to 0, and x is equal to L, C is also equal to 0, right. So, that is the boundary condition, and we have given with 4 options. See, let me write the options. A n summation over n into sine of n pi x by L into exponential of d pi square n square t divided by L square. That is the first. B is a n cos n pi x by L into exponential of d pi square n square t by L square. C, a n sine n pi x by L into exponential of d pi square n square t by L square, right. And D, a n cos n pi x by L into exponential of minus d pi square n square t by L square. So, apparently we may be thinking that we have to solve this differential equation maybe by using this separation of variable. So, it is huge, right, but for 2 marks we can think that hardly there are 3 minutes maybe, right. So, within that we have to solve this problem, or we have to actually choose the correct option, which is impossible if we start solving this equation using the separation of variable technique, because it is a lengthy procedure, right, and from there you have to get the answer. So, what will be the alternative? Alternative is you check which one of the option is matching the equation. So, if I, for example, if I take this, right, so the left hand side I will get, see, from here the left hand side, the del C del T will be equal to a n the sine n pi x by L into this exponential of d square pi square n square t by L square into d square pi square n square by L square, right, that is del C del T. And on the other hand, if we go for del C del x, I will get a n into this n pi by L, right, cos n pi x by L into exponential of this thing. So, if you further go for taking the derivative, so I will get a n square pi square by L square into sine of n pi x by L into exponential of this, and there will be a minus sign because the derivative of cos includes a minus sign. So, it is not matching, the coefficients are matching because this is getting multiplied by d. So, d n square pi square by L square, d n square pi square L square, everything is matching, but the problem is with the sign, right. So, we can think just we do not have to go for cross checking all the options. So, we have to understand that any trigonometric functions like sine and cos here, If we go for two derivatives, there will be a minus sign, right? So if you're going for two derivatives, there will be a minus sign for all these options. So if I don't have any minus sign in the exponential, the solution is not, the equation, this specific form is not going to satisfy the equation. So we will simply cross these options A and B because there are no negative signs here, right? So next, both of the options definitely will satisfy the equation. So we have to cross check with the boundary condition. Now x is equal to 0, c equal to 0, right? Which is not getting satisfied by option D because we have cos, and cos 0 is not equal to 0. Cos 0 is 1. So we have to eliminate that, and this is my correct answer. Okay. So here we are not going to solve for the expressions, but we are sorting out or identifying that which one is the correct, right? Upon this, applying the technique of elimination. So next, it's 2009 1 mark problem. It's quite simple, and this type of question has been repeatedly asked in GATE. According to penetration theory, the mass transfer, the mass transfer coefficient varies with diffusion coefficient of the diffusing species as d to the power minus half, d to the power plus half, d to the power 3/2. So you see that k is proportional to d for film theory, right? Proportional to under root of d for both penetration and surface renewal theory, right? So my option is k proportional to d to the power half. Next, this is a problem, 2009 2 marks problem, and the problem is basically associated to diffusion through variable area. What is that? Species A is diffusing at steady state. So steady state diffusion, right? Just once you start solving that problem, try to extract the information, the quantitative and qualitative informations which are important from the total problem statement, right? And species A is diffusing from a sphere of radius 1. Sphere of radius 1 this centimeter into a stagnant fluid. Right? If the diffusive flux at a distance r equal to 3 centimeter from the center of the sphere is 27 mole per centimeter square per second. So we have to understand that this is r, or rather this is r0. Here at r is equal to this 3 centimeter. Here the Na is 27 mole per centimeter square per second, and we are asked that if the radius then the diffusive flux, what we have to find in mole per centimeter square per second at a distance of r equal to 9 centimeter. PAS is the saturation pressure of camphor, that is a partial pressure at the surface of these particles, both the particles, and PA infinity, which is 0 here. So, in general, right, it is delta P, right. So, this cancels out, and sorry, there will be no K. So, we have minus of dr dt is equal to C into delta P, C into delta P by MC into 1 divided by under root of R, right. So, it is under root of R into dt is equal to a constant, let us say it is alpha, here it is dr, alpha into dt, where alpha is equal to C into delta P divided by MC, and also I think rho C will be there. So, rho C is cross multiplied, right. MC will be in the numerator. So, C into delta P into MC divided by rho C. So, that is immaterial basically, because it is not coming into that final expression. So, here we have to integrate it from R0 to 0, right, and here it is from 0 to t, or 0 to say t final, right, TF. So, this is minus R to the power 3 by 2 divided by 3 by 2 R0 to 0, which is 2 by 3 R0 to the power 3 by 2, right, R0 to the power 3 by 2, because finally it is 0 as it is complete sublimation. So, that is equal to alpha into TF, right. So, you can write R1 to the power 3 by 2 divided by R2 whole to the power 3 by 2 is equal to T1 by T2. Now, this R1, T1 is for 20, T2 is for 5. So, 20 by 5 is equal to 4, 4 to the power 3 by 2 is equal to T1 by T2. 4 cube, 4 square is 16 and 4 cube is 64. So, 64 under root is 8. So, the answer is 8. Okay. So, that is the formulation. So, basically the crux is here, this K is now changing. So, next problem, okay, there are two this 1 mark theory problem. According to surface renewal theory, the fractional rate of surface renewal's unit is the S, the unit of S it is being asked, right. So, you see that K is equal to under root of D into S, right. Renewal rate, surface renewal rate must be in terms of number per second, that's very obvious, okay, because dimensionally it should match with the penetration theory. So, S, the unit, must be in the order of t to the power minus half, right, sorry, t to the power minus 1. So, the answer is D, second inverse. So, next another theory problem, it is 2018 1 mark problem. The absorption of H2S from a mixture with hydrocarbon vapor into an aqueous alkanolamine solution, the liquid phase mass transfer resistance is significantly, so we have to compare here. So whether the liquid phase mass transfer resistance is significantly higher, lower, equal or dependent on the gas phase mass transfer coefficient. So our system is H2S plus hydrocarbon and solvent is alkanolamine, right, where H2S is highly soluble. So if it is highly soluble, the Henry's law constant must be low, very low, right, because you see y equal to mx. Okay. So if it is soluble, x is high, y is moderate but lower than x, so m must be or m is low. I can't say whether it is less than 1, greater than 1, something like that, right. So m must be low. We can say that m is much lower than 1. Okay, that can also be said basically, but that's not important. Now you see that 1 by KOY is equal to 1 by KY plus m by Kx. Now m is low, so this part is in the order of 0, we can neglect compared to 1 by KY. So it is gas phase controlling. Right. So physically also we have to understand this. See, we have a diffusion in gas phase and diffusion in the liquid phase. So bulk liquid phase, the concentration is X, the bulk gas phase, the concentration is Y. So if I have high Xi, right, in the liquid phase it will automatically diffuse, because at the interface, as the gas component is highly soluble in the liquid, we have a high concentration on the liquid side at the interface. So that specific solute will diffuse or will be transported towards the bulk of the liquid because of high concentration difference, right. But in the gas phase, we have Yi that is lower than Xi, right. So Yi, as it is lower than Xi, so definitely the driving force in the gas phase will not be pretty high relative to, or it will be lower relative to this difference or the driving force in the liquid phase, which is equivalent to Xi minus X. So Y minus Yi is much lower than Xi minus X, and necessarily it will face the higher resistance in the gas phase, right. Because if the liquid or if the specific component is highly soluble, the Henry's alternatively, we have justified it from the mathematical point. If it is highly soluble, we will have high Xi. So as Xi increases, Xi minus X increases, so mass transfer is facilitated. However, Yi is much smaller than Xi, so Y minus Yi is not that much relative to Xi minus X, right. So accordingly, the gas phase resistance will dominate. So the second, this physical example, we have basically explained it from the perspective of the driving force, whereas in the first case, it's a pure quantitative analysis from which we have got that it's stressing on the mass transfer coefficients, and from there we got that 1 by KOY is equal to 1 by KY. Right. Next, it's 2017 1 mark problem. Consider the steady state mass transfer of a solute A. So this type of question has been several times repeated in GATE. Okay. So let's see the examples. Consider a steady state mass transfer of solute from a gas phase to a liquid phase. The gas phase bulk and interphase mole fractions are, so let's draw it. So here it is YAG, here it is YAI. Right. The liquid phase bulk and interphase mole fractions are XAL and XAI. So let's have here XAI. It may be above and below, that depends on what is the value of M, right. So if M is low, which means the gas is highly soluble, XAI should be above and over YAI. And here it is XAL. Fine. The ratio XAI minus XAL divided by YAG minus YAI, what is stated, it very close to 0. So what is that? XAI minus XAL divided by YAG minus YAI is close to 0. Right. This implies that the mass transfer resistance is, and again the same similar question, the which one is governing the mass transfer resistance, whether it is gas phase, it's liquid phase, both the phases, etc., or none of the phases. So you see, we have, again I am deriving the theory which I have done in class. YAG minus YAI is equal to Kx XAI minus XAL. Because the interface, as it has got 0 mass, it cannot hold any solute, right. So even wherever the system is operating in unsteady state, the interface will be always operating in steady state. So XAI minus XAL divided by YAG minus YAI is equal to Ky by Kx, and that's equal to nearly 0, which implies that Ky is much smaller than Kx. So 1 divided by Koy, we know that 1 by Ky plus m by Kx, so this is nearly equal to 1 by Ky, right, because Ky is much smaller than Kx, that we can understand. So 1 by Ky will be much larger than m by Kx. So it is 1 by Ky, so it is definitely the gas phase controlling resistance. Gas phase controlling and negligible resistance in the liquid phase. Okay. So basically what are the options? Negligible. So this implies the mass transfer resistance is negligible in the gas phase only, negligible in the liquid phase only, negligible in both phases, considerable in both phases. So my answer is negligible in liquid phase. So this is 2016 2 marks problem. Consider the following two cases of binary mixture of ideal gas A and B under steady conditions. Right. So case 1, case 2, A, B, steady state, these are given. Right. In case 1, the diffusion of A occurs through non-diffusing B, or case 1. So 3, this is non-diffusing B, right? And in case 2, equimolar counter diffusion. Okay? In both the cases, the total pressure P is 100 kilopascal, right? And the partial pressure of A at the 2 points separated by distance 10 millimeter. So L is equal to 10 millimeter. So PA0, let's say this is Z is equal to 0, this is Z is equal to L. So this is PA0 is the partial pressure. It is 10 kilopascal, and PAL, it is 5 kilopascal, right? Assume that the fixed law of diffusion is applicable. What is the ratio of molar flux of A in case 1 to that in case B? So, Na1 by Na2, right. So, case 1, let us write the expression for diffusion of A through non-diffusing B. So, that is DAB into P by RTL into delta PA divided by PBM log mean, right. Whereas, in counter diffusion, DAB by RTL into delta PA. So, DAB cancels out, RT cancels out, L cancels out, and delta PA cancels out also. So, it is P divided by PBM, right. So, P is equal to now PBM. So, which will be PB at 0 minus PB at L divided by ln of PB at 0 by PB at L. So, you see this is going to give 100 divided by PB0 minus PA0. So, P minus PA0 minus P minus PAL, right, divided by ln of P minus PA0, because there are only two components, P minus PAL. So, this is 100, and you see here this P and P cancels out. So, it is PAL minus PA0. PAL is 5, PA0 is 10, right. 5 and 10 by ln of P minus PA0. PA0 is 10, total is 100. So, this is 90, and PAL is 5. So, PBL will be 95. So, 100 divided by 5, we include the minus, into ln 95 by 90. We shift this numerator denominator of this log. So, 20 ln 95 by 90. So, now you can solve and get the answer. So, next is, so you see a similar type of question as we have solved. Assuming the mass transfer coefficient in the gas and the liquid phases are comparable, that is Kx and Ky, they are comparable, right. So, they are in the order of each other. The absorption of CO2 from a reformer gas is CO2 and hydrogen, into an aqueous solution of diethanolamine. So, tertiary, this diethanolamine, ethanolamine, etc., they are very good solvent for carbon dioxide, right. So, once it is a very good solvent for carbon dioxide, my Henry's law coefficient M will be low, right. And as M is low, M by Kx is negligible compared to 1 by Ky, because Kx and Ky, they are comparable. So, it is 1 by Ky is equal to 1 by, nearly equal to 1 by Ky. So, it is the gas phase resistance which is the controlling, right. So, next you see this 2013 2 marks problem. 2013 2 marks problem. A study was conducted in which water was pumped through a cylindrical pipe made of sparingly soluble solid. Right. We have a pipe made of, this pipe material itself is sparingly soluble solid, right, in water. And here we have water flowing through the pipe. Right. For a given pipe and certain flow conditions, the mass transfer coefficient Kc has been calculated. So, Kc for a specific case is 1 millimeter per second for a given condition. Right, we do not know the condition yet. Using the correlation that Sherwood number is equal to 0.025 into Reynolds number to the power 0.6 into Smith number to the power 0.33. This is given in the problem statement. What is the statement? Using the correlation that we have found the Kc equal to this 1 millimeter per second. Now, if the velocity of the fluid and the diameter of the pipe are both doubled, what is the new value of Kc in millimeter per second up to 2 digit after decimal points? So, you see velocity is doubled, diameter is also doubled. So, we have to get the relation between the velocity and diameter to Kc. So, Sherwood number is Kc into diameter divided by capital D, 0.025 into Reynolds number is d V bar rho by mu whole to the power 0.6. Smith number is not changing, right. So, Kc is proportional to, here I have d to the power v to the power 0.6 and d to the power 0.6 denominator will be d. So, d to the power 0.4, right. So, Kc1 by Kc2 is equal to V1 by V2 whole to the power 0.6 into D2 by D1 whole to the power 0.4, right. So, let us say Kc1 is 1 millimeter. So, this is 1 by Kc2 and velocity is doubled. So, it is half to the power 0.6, right, because V2 is twice that of V1 and D2 is twice that of this D1. So, 2 to the power D2 by D1 is 2 and that is the statement, I think, yeah. The velocity of the fluid and the diameter of the pipe are both doubled. So, 2 to the power 0.4, so it is 1 by 2 to the power 0.2, right. So, Kc2 is 2 to the power 0.2 millimeter per second. So, you can just use the calculations and solve for Kc2. So, what is important to note here, that you have to understand the expressions of Sherwood number and Reynolds number and both containing d here, that is important. If you miss that d, you will get a wrong answer. Okay, the same again the solubility and the here not the gas phase or liquid phase mass transfer resistance, which one is to be controlling, that is not the question, but here we have to draw the profile of concentration. This 2011 2 marks problem. What is that? A gas mixture is in contact with the liquid component, with a liquid component P in the gas mixture is highly soluble in the liquid. So, that means M is low, right. Concentration profiles during adsorption of P are shown in the choices, where X, it is conventional, X is the mole fraction of P in the bulk of the liquid, Y is the mole fraction of P in the bulk gas, Xi, Yi are the interfacial concentration, Y star is the equilibrium gas phase mole fraction corresponding to xi, right, corresponding to xi. Okay. No, corresponding to x, I think, x, the bulk. The correct profile is, so what are the options? Let me draw this, whatever is given. yi, xi, y, x, and here y star. That's option A. Option B, this, y, yi, y star, xi, x. C, yi, y, xi, x. Here is y star. And option D, this is somewhere here is y star, y, yi, xi, x. Now you see that close to that interface concentration must undergo a fall, right? Why this fall is necessary? Because close to the interface we have laminar sublayer where the resistance is pretty high, okay? And because it is diffusive resistance, and far away from the interface we have the turbulence, so it is the convective plus, or more majorly it is a convective resistance. So convective resistance is much lower than diffusive resistance. So if I have to maintain the same flux here and here, right, we need a higher driving force here compared to the bulk region. So driving force is the change of concentration. So definitely concentration must fall close to that interface on this gas side and must again fall towards the bulk in the liquid side if it is a process of diffusion from the gas to the liquid, or process of this mass transfer from the gas to the liquid. So this can never happen, right? And this also can never happen. So we have to choose between A and D, right? Now M is low. M is low means we have y is equal to, or yi is equal to mxi, correct? So if M is low, xi must be higher than yi, and y star is equal to what? Mx, okay, mx. So y star must be lower than x, obvious, because M is low and lower than 1. So this can never happen. Here xi is lower than yi and y star is higher than x, but here xi is higher than yi and y star is much lower than x. So A is the option. So one thing is to be very clearly understood, that you don't have to mug up lot of equations, right? In mass transfer, maybe very hardly, if we just collectively think, it may be hardly 10-15 equations, not more than that, in the entire chapter of mass transfer, or entire the subject of mass transfer, right? But you have to conceptually understand, particularly you should understand the theory from its geometry, okay? So next question. This is 2010 2 marks problem. At what is stated? At 25 degrees Celsius and relative humidity of 90%, water evaporates from the surface of a lake at a rate of, this is this m dot. Water evaporates from the surface of a lake at a rate of 1 kg per meter square per hour, right? The relative humidity that will lead to an evaporation rate. Now if I change, so this is m1 dot So this is HR1, right? Relative humidity, which will lead to an evaporation rate of 3 kg per meter square per hour, with other conditions remaining same, is 30%, 50%, 60% and 70%. So you have to find out HR2. Right. Now you see m dot is equal to ky. Say we have the surface, this is water, this is air, and here this is yi, this is y. So you can write it is ky into yi minus y, and that's equal to Na, the molar flux, correct? That's the molar flux. So this we have discussed in this chapter of humidification. So ky, and now y. Y, how we can write in terms of H, the absolute humidity first, or rather maybe the it's relative humidity. And how the relative humidity is defined? It is Pa by Psat into 100, right? So we can change it to Kp into Pasat or Pai, which is Psat. Here this partial pressure at this interface is a saturation pressure, and far away it is Pa. So Psat minus Pa, right? So m dot is equal to Kp into the molecular weight of water. Now if I take this Psat common, temperature in both cases remaining same, Psat common, so you can write 1 minus this HR divided by 100, right? So m dot 2 by m dot 1 is equal to 1 minus HR2 by 100 divided by 1 minus HR1 by 100, right? So this is the ratio is 3:1. So 3 into 1 minus HR1 by 100 is equal to 1 minus HR2 by 100, right? Because that's 3, that's 1, and HR1 is 90%, so 1 minus 0.9, so this is 3 into 0.1, so that is 0.3, 1 minus HR2 by 100, so HR2 by 100 is equal to 1 minus 0.3, that is 0.7, so HR2 is equal to 70%. So that is my answer. Right? So the option is D, because the options given are 30, 50, 60 and 70, so it is 70%. Next, this is 2008 2 marks problem. A sparingly soluble solute in the form of a circular disc is dissolved in an organic solvent as shown in the figure. So what is the figure? It's like this. This is the sparingly soluble solutes disc, right? And here we have the organic solvent in which the solute is dissolving. The area available for mass transfer from the disc is A. This is A. The volume of the initially pure organic solvent is V. So V, and we have to note that C at 0 is equal to 0. The disc is rotated along the horizontal plane at a fixed RPM to produce a uniform concentration of the dissolving solute in the liquid. So it is basically a lumped parameter system, or lumped parameter approach we have to go for, because the concentration everywhere is constant. The convective mass transfer coefficient under this condition is Kc. The equilibrium concentration of the solute in the solvent is C star. So obviously just at the interface between the disk and the organic solvent we have a concentration C star. The time required for concentration to reach 1% of the saturation value is given by, there are 4 expressions. So we have to find out the time, or say T1, such that C at T1 is equal to 1%. So basically 0.01 C star. Okay, we have to solve for that time. So if you just write an unsteady state balance, I will get that plus of, rather it is V into dc dt, that is the amount, the rate of accumulation of that solute in this organic solvent, right, and that's equal to the rate of mass transfer, which is Kc into C star minus C, that's the driving force, into area, right. So dc divided by C star minus C, integration from this C equal to 0 to C equal to 0.01 C star is equal to Kc into A divided by V into T. So here it is minus of ln upon integration C star minus C, and that is C equal to 0 to C equal to 0.01 C star, that is Kc into A into T divided by V. So what is going to happen? C equal to 0 in the numerator, so ln C star divided by this 0.99 C star, so that's equal to ln 1 divided by 0.99, right, because C star cancels out, equal to Kc into A into T divided by V. So my answer is pretty simple here, exponential of minus of Kc, because this log of 1 by 0.99 is minus of log 0.99, right. So minus, we switch to this side and take an anti-log, so I will get Kc into A divided by V into T equal to 0.99. So this is option A, and that's the answer. Okay. So that's all for this session. So next session we will continue solving more problems, and we are moving towards this other standard mass exchangers. Thank you.